Great. Okay, hello everyone. I'm Srijan Das from UNC Charlotte. I'm an assistant professor in the Department of Computer Science. And today, the event is about Best of WAGV 2025. I will be just presenting one slide from what we contributed in WAGV 2025, and rest of the slides are related to our research and Navididan, which is large language vision model for daily activities of living, which will be presented next month in CVPR 2025. Before I dive into Navididan, I would like to give an overview of what we are doing at UNC Charlotte in CharMLab. Yeah, okay. So our long-term objective is basically to monitor older adults and their activities in their home. And this can be done through ego glasses or monitoring cameras. What do we want to capture through that? We want to capture different modalities. It can be audio. Most importantly, it should be visual information coming from RGB sensors, or it can be information coming from depth sensors. And what do we want to do with these modalities? We want to develop a computer vision model. Since the objective is to work with older adults, we would like to have geriatricians in the loop so that the computer vision model that we develop takes into consideration the things that a geriatrician looks into. And once we have this kind of computer vision model, can we get a language-based word state history, which basically logs what activities are performed by the older adult at which timestamp in which place in the indoor scenario? So all these things are going to happen inside the house. And once we have this is how the language-based word state history looks like. There's actually a clip taken from Socratic models from Google. And basically, if you have a good vision language model, you can pretty much understand what is the place, what are the objects the person interacted with, what is the activity the person is doing. And this is the kind of information we are looking at. And what do we do with this information? We can give it to the clinicians, which can be used for personalized care, tracking their cognitive decline. So basically, if we are able to do this, probably we can enable 24/7 automated ADN assessments, which can be of importance to medical practitioners for longitudinal studies of aging, which is kind of missing in the community at this point of time. So let me now tell you what problems we are looking at. So basically, to do video understanding, we have to solve a problem called action recognition. And it's a very simple problem under supervised setting that we have videos. Each video has some action which is like labeled. So you can consider it as a simple problem where a clip of 10 seconds and a person is performing some sort of activity. You train a model with this kind of data, and basically you are learning the mapping from the input videos to the action labels. So basically you are coming up with discriminative video representations. But ideally, you would like to extend it into a framework where you can deal with untrimmed videos, where you are handling 40 minutes or 1 hour videos when the actions are performed one after the other or at the same time, and your model should be able to tell you what are the actions performed at which timestamp. But in order to solve that complex problem, you need to solve this fundamental problem of classifying actions given a small video clip. So video representation learning is not new for the vision community. It's very popular. We are specifically looking into activities of daily living. This is a glimpse of a data set called Toyota Smart Home, which we have captured back in 2016, where we asked 18 elderly people to stay in an apartment and we recorded them for like 8 hours. And you can see the setting over here, the camera installments. These are on RGBD sensors. We recorded them, we had the data, and we annotated them with the kind of activities we were interested in. And we have two versions of this data set. One is the trimmed version where we have around 16,000 videos with 31 actions. And then we have TSU, which is the untrimmed version of the smart home, where we have 536 videos, but most of these videos spans like from 40 minutes to 1 hour in terms of the duration. And there are 51 activities. So these are some activities we are interested in because these are the activities usually we perform in our daily lives. And remember that these are very boring videos. Um, these are not easily available on the web because you won't see videos where a person is watching TV or using laptop for hours or reading papers for hours. In the web, you will be getting interesting videos where you have prominent motion. And that's where the challenges in Alien lies. In Alien, um, actions are performed very spontaneously. There is no script that you are following. Most of the existing models that we have in video understanding are usually trained on web videos where you can actually just look into the background and say what kind of activity is being performed. Like if a person is swimming, let's say taking a sports action, you can just look into the background and say the person is swimming. You don't need to understand the motion. And sometimes the motions are perforced. They are very prominent and the modern can easily capture or catch up those motion. Since internet videos are captured by cameraman, you they ensure that the subject is always at the center of the frame, which is not true for Alien because you have monitoring cameras and the subject can be anywhere in the video. So the resolution of the person in the video is pretty bad, and you can have occlusions, you can have long-tail distribution of activities, which means some actions are more common than the others, but that is how it should be. So there are many such challenges, and since most of the current AI models are trained on web videos, they don't actually address the challenges in Alien. So they don't work very well when we try those models on smart home kind of data sets. So as I said, there are many challenges, but there are some more fundamental challenges which we are interested in solving. And one of them is how to handle time. And it's a long-standing question. Um, if I would present this back in 2020, I would say that, okay, previously we used handcrafted features, then LSTMs, 3D convolutions, but now things have changed. With new architectures, we have come up with better ways of modeling temporal information in videos, but we are still exploring that area, that how we can handle time in videos or how we can model temporal information. The other question is how to learn view invariant representations, since the cameras can be installed in different positions. And most of these architectures that we use are not view invariant. These are 2D information that we send to the models. So we need to really learn some sort of view invariant representations. And finally, there are activities in ADN which have very subtle motion, like cutting bread or using tablet. And we have to know these representations, or we need to model these subtleties in the videos. So fine-grained understanding of the videos is also very important. So when coming to how to handle time, as I said, in 2020s, I would say that, okay, before 2020s, 3D ConfNets, like i3D, 3D versions of ResNet, SnowFast, these were very popular, where you have these spatiotemporal kernels that convolve across the entire video. And after 2020, we had video variants of transformers. So there were this time S former, video swing transformer, MAE version of video, Vivid. On these are transformers with spatiotemporal attention mechanisms that and these attention mechanisms can be like you can dissociate the spatial and the temporal attention into these VITs just to save the FNOPs or the compute complexity of the transformers, since they are directly proportional to the number of tokens you are using for computing the self-attention. So yeah, the transformers have become very popular in using as backbone for visual understanding. And now in 2025, I would say that, okay, whatever is the architecture, you need to use something like foundation model. So if you have some variant of a video variant of CNIP, because CNIP is trained on like millions of data, we would like to use that kind of architecture because it utilizes large scale pre-training. So it has very good understanding of the images, the objects in the images. And what we need to make sure is that we can also have some temporal understanding. So the video variants of the foundation models like CNIP are now becoming popular, and that's something that we are using as backbones nowadays for video understanding. But this is how time is handled on this kind of problem statements. How can we learn view invariant and fine-grained representations? And that's where I have been working on for many years, that how we can use actually 3D poses of humans to enforce the model to learn fine-grained representations. And the good thing with 3D poses is that it is robust to illumination changes, it's view invariant since it is 3D, and it also provides geometric information associated to the actions. Previously, we just relied on depth sensors to get this kind of high quality 3D poses. But now you have RGB algorithms which can extract very good 3D poses like the ones here. NCRNet and Video Pose 3D, these are algorithms that work on RGB algorithms. And if you combine 3D poses and RGB, you might actually enforce the RGB encoders to focus on the areas where the action is happening. And that's where you can address the challenge of fine-grained representation learning. So RGB plus 3D poses are something that we have been working for years now. Back in 2021, there is this TPAMI paper, VPN++, where we combine RGB and 3D poses using knowledge destination so that we make sure we don't need these 3D poses at inference. Then last CVPR, we presented a variant of this RGB plus pose algorithm in video transformers. And this year in AAAI, we presented how RGB plus poses can be used in the CNIP embedding space, because CNIP embedding space is a vision language embedding space, right? You have only RGB and language. How can you integrate 3D poses into this embedding space without hampering the discriminative representations that you have already learned? So this area is kind of explored by our team. And then in this year, only this year, we saw this challenge, Enter the Action Recognition Challenge in WAGV 2025. And the challenge was pretty simple, that you can use whatever data you want to train your model. And basically, given the test data, you need to classify them into 6 action categories. And these are the action categories which were given. And these actions are pretty much composite action labels. The associated fine-grained labels were also provided. And we just used a foundation model like a video variant of CNIP. And we trained that model on different data sets. And we kind of secured the third place in this challenge, and probably that's the reason I'm giving this talk. But this is the only slide that I have for this challenge. And I would just give the conclusions of what we observed in this challenge is that when we are dealing with activities of daily living, person-centric cropping is very important. We don't need the background information because everything is done in the indoors. If you are in the kitchen, your human object interactions will make it clear that you are in the kitchen. Um, Zero shot moderns, we talk a lot about those kind of moderns, but they are not that effective. Training moderns, videos closer with target domain, hence scaling the data, hence. And that's what we see that when we scale up the data, we use smart home and etri as our training data set. When we use person-centric cropping, that's where we get maximum accuracy. Um, and what we understood is that these models are limited to the action labels that we are training them with. We wanted to go beyond that, and we need some good multimodal LLMs because now we are talking about things after 2023. Because the era of transformers and clip, those are gone now. People are working on how to integrate videos into the LLM embedding space. And our question was that, okay, let's see how the current multimodal LLMs are working with this kind of alien kind of data. So this is a paper video chat GPT. We just used their demo. We fed an ADL data. We asked questions related to the activities performed in this video, and the model completely messes up. Let me show another example where a person is near a closet taking medicine, and then the person will use his telephone. And when I ask what action is performed, what are the actions performed, it says like opening a closet door, pulling out a book, reading it, and then putting back um, the book in the closet. So basically, the modern hallucinates that if the person is near the closet, probably the person is using books because that's the kind of data the model might have seen. um, and clear need doesn't understand motion or the objects in the video. And that's where we understood that these multimodal LLMs don't understand ADN that well, and we need to come up with our model, or we need to train it with our data to make these models work on understanding activities of daily living. And in order to do that, there are three steps. First is we need data because most the data is like you have videos and action labels. You don't have visual instruction pairs that will enable the training of these models. And once we have the data, we have to come up with the model and train that model. And once we have the model, we need to test those models. So we need to have a benchmark suite. And that's where we have three contributions. One is the ADNX data set that we come up with. Then we have the model, which is Navididan, which is kind of a multimodal model, which goes beyond just videos and text instructions. And then we also come up with a benchmark suite, which is ADNX benchmarking. So coming to the first part of the data set that we curate. So we don't come up with a new data set. It's just like we use a public data set and generate the descriptions or question answer pairs, the visual instruction pairs that is required to train these kind of multimodal LLMs. So most of the data that we have used spans 3 to 4 seconds. And that is not something that we want because the model should be able to process videos of 30 minutes or 40 minutes. For that, they need to have long understanding of the video. So we take these trimmed videos. We first decide that, okay, how we can concatenate these videos to make a long video. So we ask LLM that, hey, can you give me a sequence of actions which are more likely to happen in your daily life? Once we get that, we take those clips And what we do is we do a person detection. Why do we do a person detection? Because we are not interested in learning what is there in the background, but we are interested in learning what the person in the video is doing. So when we generate the data, like the instructions, we want the LLMs to focus more on the person and their actions. Once we have that, we just do a temporal stitching, which is basically just concatenating the videos to create a long video. And once we have that, we sample some of the frames from this long video. We use an image captioner to generate captions per frame. And then we take those captions, give it to GPT, ask GPT to summarize the video. And once we have these video descriptions, we know the actions that are performed in this long video. That's why we say that there is a weak supervision. And we take this information and give it to GPT again to generate question answers. And there are different categories of how these generation works. Like we want to have spatial understanding, we want to have temporal understanding, we want to have questions related to the activities performed in the video. So that's the semi-automated data curation framework that we come up with. Once we have that, then we need to come up with the model. So usually the models are like you take a video, you send it to the model. The model is you have a visual encoder that will give you the tokens from the video. And then you have a visual connector, which will adapt these tokens into the LLM embedding space, and then everything goes into the LLM. However, these models don't work that well with ADN. So we come up with our model where it's basically the same architecture, but we have some additional cues. Additional cues specifically to address the challenges of ADN. So these additional cues are human object interaction cues and the 3D poses. So how do we get these HOIs, the human object interaction and pose cues? So for the HOI features, take a video, then we do some frame sampling, like this can be a simple uniform frame sampler. Then we do object detection, and it can be your favorite object detector like YOLO. We used BNIP2 for this. Then we do a object filtering. That means we know the action performed in this video since we have this weak supervision. And from that information, we ask GPT that, okay, if these are the objects in the video, what are the objects related to these action sequences? And we just take those objects. Once we know those objects, like the relevant objects for the activities, we localize those objects using our V2. We get the features associated with the objects, and then we do a tracking. So we get the HOI features. Once we have that, the next thing is we need the pose features. For that, we actually follow our work from OpenAI 2025, where we came up with this pose knip. Pose knip is a dual encoder framework. It is like how knip works. So you have a pose backbone, you have a text encoder. This text encoder is initialized from the knip model. So first you train the pose backbone so that the pose backbone has some pose representation learning for actions. And in the second stage, you fine tune it to do this alignment between the pose features and the language descriptions. And once you have that, you just take out the pose features from the pose backbone. And that's the feature you are going to integrate into the LLM space. So the next question is that, okay, you have these different modalities, text, videos, poses, HOIs. How do you want to integrate them all together? Because when you try to do a joint training, the challenges are that you come up with conflicting gradients. And for that, we come up with a multimodal progressive training where you increase the complexity of the problem slowly and progressively. How do you do that? By integrating the modalities one after the other. You start from the very basic one, and then you start increasing the complexity, for which we use curriculum learning. So in stage one, you first integrate the modalities independently. Then in stage two, um, so in stage one, we decide that, okay, videos are the easiest tasks to do because the loss is very low as compared to the other modalities that you get. Then you take the video model and you integrate the object queue and you take the parameters from stage one, and then you jointly train this model. And finally, then you integrate the pose, which makes the problem much harder, and that's how we do the integration. And this is determined by the curriculum learning strategy that we used. So that's the multimodal progressive training strategy that we use to train our model. So to once we have the model, we need to benchmark this model. We need to validate the effectiveness of this model. So for testing, we have data sets coming from distribution, which is very different from what we have used in the training. So for which we use Charade, Smart Home, NEMA, Toyota Smart Home, and the tasks that we perform is AD and MCQ tasks, where we use where we ask the VNM questions related to action recognition or temporal completion task. And we also evaluate the model on video descriptions. So this is a sample of a video input to our model, and you ask the model to describe the video. And these are the state-of-the-art models compared to what our model is uttering. In the paper, you will also find a comprehensive evaluation of different models, and we have the state-of-the-art results in most of these tasks. And it's interesting that in Navididan, where we just use 100K question answer pairs to train our model, outperforms many other models which are using millions of question answer pairs. It does pretty well on action recognition, action forecasting, video description, and it can also process very long videos. This is a demo that we have. So this demo is actually performed on an upgraded version of our model, because the LLM that we used in the paper is Vicuna, but now we are using Quen, and the visual encoder that we were using in the paper was Knip. Now we are using Signip. So yeah, you can see the kind of results that we are getting. So yeah, that's all from my side. So since I showed you this example, I just want to say that, okay, we solved this problem. Now the model can understand fine-grained information in the videos. It can also do action forecasting. And all this work has been done by the students, Dominic, Orko, and Manish. So yeah, thanks to them. If you have any questions, please.
It does look like we have two questions. First question came in early in the presentation. Are poses which you are trying to detect are positions and orientations of persons, or positions and orientations of the parts of their bodies? How do you represent a pose?
The poses are the 3D coordinates of the human joints, basically. So there is a domain called skeleton action recognition. It's very easy to extract the skeletons either from Kinect, or there are other RGB algorithms. So you can basically get 17 joints or 25 joints, depending on the algorithm you are using. So you just use these coordinates, and then you can do some pre-processing, and you can feed it to the post backbone. So yeah, basically that's what you need.
And then an additional question here is, and this one came right around when you were talking about benchmarking on ADL tasks, is what actionable conclusions do you hope the system will provide, and on what time scale?
I see. So what we have seen is now the model can give us information of what exact activities the person is doing in the video. After upgrading these models, now we can see that you can actually ask about the scene. There can be multiple person in the video. There can be multiple actions going on. And you can ask questions, all questions related to that. While we have in this work, we have focused on understanding activities of daily living, but in practice, people from different domains are actually interested here. Like people want to know what is happening in the factories, what is happening in the banks, what is happening in surveillance scenarios. Domain specific training is something very important. That is what we learn from this work. So we have to understand that what a downstream task you want to solve. And that is how you can use this framework to train your models for your domain specific task. And that is something important to understand. Like I feel like, okay, we can come up with a generalized model, but the generalized models are not going to answer to the questions which are very domain specific, and that's where domain specific training is required. And so it really depends on the users and the application you're targeting.